Rotating a motor requires few controls. This document will introduce 4 general controls and RX MCU peripherals that enable them. These 4 controls could be roughly divided to 1. PWM output to control inverter switches for 3-phase sine wave generation. 2. Feedback input of encoder and shunt current to calculate current motor position and speed. 3. Computation ability to calculate control parameters, based on feedback input, to drive motor's parameters, such as speed, to the command value. 4. Safety function to prevent system failure due to high current because of the negative and positive phase switching are on at the same time. This document also explains which RX MCU peripherals could be used to implement these controls. RX MCU has 2 high-performance timers, MTU and GPT, that could control PWM output. MTU is a high-reliability timer with a long track record used in the SH-MCU family. GPT is, in terms of functionality, a MTU timer with extended functions. The timer counter of MTU and GPT are 16-bit and 32-bit respectively. Both timers could output various complementary PWM waveforms required by inverter control. Furthermore, they can output 0% and 100% duty PWM and dead time control. GPT supports high-resolution PWM generation function. This function can output PWM waveform with a minimum resolution of approximately 195 picosecond, allowing finer control. In addition, it is also possible to output U phase, V phase, and W phase waveform out phase to each other. Here is the explanation of complementary PWM waveform generation by MTU and GPT one by one. MTU uses the combination of 2 triangular featured counters, one for the positive phase and another for the negative phase. By combining with U phase, V phase, and W phase dedicated compare-match timer, each phase of 3-phase complementary PWM is symmetrically outputted. The width of dead time is automatically generated by setting only one dedicated register. It is super easy to set up and has long been a favorite feature of users. In the contrast, GPT has extremely rich PWM carrier options, with 4 modes of triangular wave and 3 modes of sawtooth wave. Each waveform of 3-phase complementary can be set up individually. Therefore, U phase, V phase, and W phase waveforms could be generated out phase of each other. The dead time of complementary PWM waveform could be adjusted on matching between counter and compare registers value. The value of the compare register could be updated during CPU interrupt routine generated at the trough or the crest of the counter. However, if the update is set both at the trough and the crest, the CPU workload is increasing, causing the duty update might not to happen at required timing. To avoid this problem, both MTU and GPT is equipped double buffer function that could set duty update 2 times at only one CPU interrupt. The feedback data, such as angle and speed, could be obtained from angle sensor or the current flowing in the motor. When the current or analog output of angle sensor is feedbacked, AD converter is used. In contrast, when the feedback is from a digital outputted sensor such as an optical encoder, the phase counting mode of MTU and GPT or serial module is used. Here is an explanation of how the current detection works. Each current of U phase, V phase, W phase is detected by measuring the current flow of shunt resistors. In this case, it is required to acquire the current value of each phase at the same time. To support this, RX 12-bit AD converter is configured with 3 channels of sample and hold circuit in the front stage and 1 channel in the back stage. At first, the 3 channels of the front stage sample the currents of U, V, and W phase at the same time. Then, the channel of the back stage will convert sampled date of U, V, and W phase sequentially. By this, the AD values of U, V, and W phase are acquired at the same timing. In addition, the AD converter is equipped programmable gain amplifier, so an external amplifier for current detection could be eliminated, reducing the number of parts. In case the position and angular speed are measured by the phase differences of the digital signal of A phase and B phase like an incremental encoder, the phase counting mode of MTU and GPT is used. When the ABZ output type encoder is used, the Z phase is assigned to a pin interrupt. MTU has a 16-bit or 32-bit counter, and GPT possesses a 32-bit counter. There are pins for pulse inputs for the A phase and B phase of the encoder. The phase relation of the rising and falling of two input pulses drives the TCNT counter, which then could be used to acquire the position data. The phase counting has a maximum of 15 types of pulse counting modes, supporting a wide range of encoders. In addition, an input capture function is also provided to measure pulse intervals to determine speed. The RX72T is a high-performance microcontroller for motor control that operates at up to 200 MHz and achieves 1200 core mark score. This is 1.5 times faster than ARM Cortex microcontrollers operating at the same 200 MHz. In addition, it has several hardware modules that enable faster operations and processing, such as a floating point arithmetic function, trigonometric function arithmetic unit, and register bank save function. The register bank save function is a hardware function that saves CPU register information when an interrupt occurs. Up to 16 banks could be used and it could support frequent interrupts. By using the register bank save function, the response time to interrupts can be dramatically reduced from 27 cycles to only 6 cycles. This enables improved CPU processing performance. Both floating point and trigonometric operators are hardware supported. The performance is significantly improved by up to 8 times for floating point operations and up to 6 times for trigonometric operations. This significantly dramatically shortens processing for time-consuming operations such as vector control and accelerates the overall operation of the application. The RX also possesses functions that are very effective for motor safety, such as inverter control, short circuit prevention, and overcurrent protection. A typical example of this function is the port output enable function, here by PoE. Since high voltages are often applied to motors, serious damages could occur by such phenomena as abnormal motor current, overcurrent due to a short-circuited inverter circuit, and clock abnormalities. The role of the PoE is to quickly detect the occurrence of abnormalities and safely stop the motor. PoE are broadly classified into PoE and PoEG. PoE is compatible with both MTU and GPT. PoEG is dedicated to GPT and, unlike MTU, the combination of output terminals to be forced to stop could be set up freely. Here is a more detailed explanation of the PoE function. As described earlier, PoE has a mechanism for detecting the 3 abnormalities. The first is the detection of abnormal inverter output current. The output current goes into AD converter and on-chip comparators monitor whether the current value is abnormal or not. The second is the abnormality detection in control signals to the inverter. The complementary PWM waveforms output by the MTU and GPT are constantly monitored to immediately detect a short circuit due to a runaway program. Third, as for clock abnormality detection, PoE constantly monitors the clock frequency of the microcontroller and detects abnormalities at any time. In addition, PoEG can also suppress control signals to the inverter directly by an external signal input. This is for when users detect an abnormality in external devices and force the motor to stop as soon as possible before the microcontroller detects the abnormality. What do you think about RX peripherals for motor control? We have prepared more detailed explanatory materials and sample codes for the functions introduced so far. Please feel free to refer to them as they are available for free download from our web page. We have also prepared completed software and solutions for motor control. Please refer to them as well.